Good afternoon, class. We are looking at module 3 practice test, which is about chapters 5 and 6, polynomials and rational functions, exponential and logarithmic functions. Let's start with the first example, the price demand function of a company that manufactures a large tank is given as P of x equals minus 5x plus 600. We want to find the revenue function. So just to remind you, the revenue function is the product of the price times x, the number of units times the price. So we find this to be minus 5x squared plus 600x. The company's fixed monthly cost is given as 1,563, and each unit will cost 10 bucks. We want to write the cost function using, in essence, mx, okay? So the cost function is 10x plus 1563. Profit function by definition is revenue minus cost. So far, fairly elementary. How many units should we produce and sell to maximize profit? This is a quadratic function. Where A is negative. More specifically, A is -5. So if we were to graph this, it will open down. It's a parabola that opens down. So the maximum occurs at its vertex, x equals minus b over 2a. The maximum occurs at vertex where b is 590 and a is -5. So minus 590 over 2 times minus 5 gives us 59. The maximum profit, put it into the profit function. Price, put it into the price function. So take a look again. I want to make sure everybody is comfortable with that. We found the profit function. So we put that in there for the profit function. And here's the price function. We put the number that we found into the profit function so we can see the answer. $305. Okay, it's pretty straightforward, class. Here's a polynomial of degree 3, has a root of multiplicity 1 at x equals minus 6 and a root of multiplicity 2 at x equals 4. So we are going to write it as a times x plus 6 times x minus 4 because the multiplicity is 2 squared. It goes through the pair, so we are going to replace the x with 2 and y or p of x. Y or p of x with 8. This is 8. This is minus 2 squared becomes 4, and a becomes 1/4. So here's the function. Divide. We can do long division, we can do synthetic division. Because we are dividing by x plus 1. Here's how we get that started. We put this in order: 3 minus 2, 1, negative 4, and this one x plus 1, we put minus 1. If it's x minus 1, we put positive 1 here. So in general, if it's x minus k, k goes here. So the general format x minus k, then we are going to put the k here. The other thing that is important with the synthetic division to remember is that we have to have everything in order. So any term missing, we must replace it with 0. For example, negative 2x squared is not there. We must put a placeholder 0. So we drop number 3. So here's how we get that. We drop number 3, the first one. Then we multiply by k. We add them up. We multiply by k. You can do this, multiply by k, which is negative 1. Again, k, which is negative 1. Add them up. Multiply by k, which is negative 1. Add them up. And there you have it. Take a look at what's going on here. So we get 3, negative 5, 6. Now the exponent is 3. We are dividing by x plus 1, so it goes down by 1. X cubed becomes x squared, and you move on. 3x squared minus 5x plus 6. And the last one is your remainder. You can say plus and put this at top of x plus 1, the divisor, or change it to minus 10 over x plus 1. Makes no difference. As long as you understand the meaning, you're in good shape. We are given the following function. We want to list the possible rational zeros. If you recall, the way we find it, rational zero says factors of a sub 0, in this case is number 3, over factors of a sub n, in this case is number 2. So factors of 3 are 1 and negative 1, 3 and negative 1. Factors of 2, 1, negative 1, 2, negative 2. So in other words, if we were to write it in this fashion, we could say the top is plus minus 1, plus minus 3. The bottom is plus minus 1, plus minus 2. And that results in those numbers. Plus minus 1 over plus minus 1, plus minus 1 over plus minus 2, plus minus 3 over those. These are the answers. Now we want to find the rational zero. The process is that you keep on putting these numbers until you get a 0. I'm not going to go through the process, but if you plug in number 3, it results in 0. Therefore, 3 is a 0. That means this is divisible by x minus 3. That's the meaning of it. To find the remaining, we have to divide this by x minus 3. I'm going to assume everybody can do that either using the long division or a synthetic division. This one, you have to find the zeros by the quadratic formula. By the way, if there are more rational zeros, you can plug in the rest of them and see what else is there. But there happen to be none. And the only rational zero is 3. Using the quadratic formula, everybody remembers the quadratic formula, right? Let me just again quickly remind you of that. Ax squared plus bx plus c equals 0. X is minus b plus minus the square root of b squared minus 4ac over 2a. And so we can write them in the following manner. The first one was x minus 3, then this one x minus 1 minus square root of 3 over 2, x minus 1 plus square. So square root of 3 over 2. Pay attention to the way we write it. Here's the function. We want to find f of 1. We want to find f of negative 3. I'm going to assume everybody knows what that means. Plug in 1, evaluate. Plug in negative 3 into the function and evaluate. When we do that, both of them result in 0. What does it mean? It means x minus 1 is a factor. X plus 3 is a factor. That's the meaning of it. If we were to use rational zeros, and we're not going to do that, we need factors of negative 75 over factors of 1. Of course, factors of 1 is just plus minus 1. In essence, it's just the factors of the numerator negative 75. So there will be a lot of numbers. I'm assuming everybody can see what's happening here. Plus minus 1, plus minus 3, all the way to plus minus 75. And you have to figure out what the answer is by plugging in. We already know f of 1 is 0. We already know f of negative 3 is 0. And if we were to use the technology, you can go with the graph, second calc, 0, or try 1 by plugging in and finding 1 and negative 3, because in case they ask you for technology, it can be done by finding the zeros of the graph of the function. If 5i is a 0, find the remaining zeros. Okay. Number 1, this is degree 4. That means there are 4 zeros. Some of them they may be repeated, but there are 4 complex zeros. 2 of them happen to be real. If 5i is a solution, then by the conjugate theorem, also a minus bi is a solution. So if the polynomial with real coefficient has the following a plus bi as a solution, then its complex conjugate, which is a minus bi, is also a 0. So because it's 5i purely imaginary, also negative 5i is a solution. Therefore, we can write it as follows. If we were to factor them, we know we have x plus 1, we have, my apologies, x minus 1, we have x plus 3, and now this x minus 5i, x plus 5i. Now, you can leave it like that, but these two, I hope you realize it's x squared plus 25. X squared plus 25. A squared, which is x squared. Let me write that. A squared, which is x squared, minus b squared. Okay, which is 25i squared with the negative. Because I squared is negative 1, we get plus 25. Okay, here's the next one. We want to find the domain. And to find the domain, all you have to do for a rational function, set the denominator equal to 0 and exclude that. So whatever makes the denominator 0 is out. Factor. So x either negative 2 or positive 4. Those two are out. How do we write them in interval notation? Minus infinity to negative 2, union negative 2 to 4, union 4 to infinity. That's how we exclude those two numbers with parentheses. That means every number from negative to positive infinity is okay except those two. Want to use the remainder theorem to evaluate this at x equals to. Basically, it means plug in number 2. Whatever the answer is the remainder. I'm assuming everybody can do that. So 6 times 2 to the power of 4 minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. You do the math, you end up with 25. Now, if by any chance this is 0, this becomes the 0 factor theorem, which means x minus 2 is a factor of this function, which is not, because it's any number other than 0. Show that x plus 2 is a factor of this guy, and then find the remaining factors using the factors to determine the zeros of polynomials. Okay. If this is a factor, that means I can divide by it. And one easy way with the factor theorem, I'm going to plug in negative 2. If I plug in negative 2, I must get 0. I'm going to leave it for you to show that. And that really takes care of the first part. Plug in negative 2, and show that it's 0. But to find the remaining factor, we have to divide by x plus 2. And I'm going to leave that for you using any method, including the synthetic division. So what does that mean? It means this function is equal to x plus 2. Now it's going to go down by 1. So 1 times x squared minus 8x plus 15. And this, notice, the synthetic division gives us 0. Factor theorem gives us 0. So you write it in this fashion. So this will translate into the second parenthesis. Now, the second parenthesis we can easily factor out because we want two numbers. The product is 15. The sum is negative 8. So this is the factored format. Now, we found the factors, x plus 2, x minus 3, x minus 5. Now use them to determine the 0. So the 0 would be negative 2, positive 3, positive 5. Here's a function. We want to find the domain in interval notation. Basically, you set the denominator equals 0 to find the domain. But in general, whenever you want to graph a rational function, number one, put it in lowest term if you can. So it's a good practice to factor things out. So when we factor things out, this is what happens. X plus 4 drops, although it has no bearing on the domain. I want you to know the domain remains unchanged, meaning we can't have negative 4, we can't have negative 3 halves. But it does have an effect as far as the shape of the graph is concerned. So it is equal to 1 over 2x plus 3, and x can't be negative 4. So what is the domain? As I mentioned, x can't be negative 4, x can't be negative 3 halves, and we write it in this fashion. Asymptotes, holes. Well, as far as a hole concerned, if we go back to this, what this really tells us that because we have a common factor, that creates a hole, because x can't be a specific number, negative 4 for this one, but it can be for this one. So if you were to graph this function without paying attention to this, there is no hole there. But this means x can't be negative 4. Now you are going to put the negative 4 and evaluate the f of x or the y coordinate. That means at negative 4, negative 1/5, the graph has a hole. So again, I want to make sure everybody understands what's happening here. When we look at the factored form, because of the common factor of x plus 4, and we drop it and we write x can't be negative 4, at x equals negative 4, the graph has a hole. So roughly that's the location. And here's the idea behind the asymptotes. As far as the vertical asymptote, not over here, you have to look at here, the denominator equal to 0. So x equals negative 4 is not an asymptote, it is a location of a hole. So denominator equal to 0, x equals negative 3 halves, that is a vertical asymptote. How about the rest of them? If you recall, we have the function in this format. You look at the degree of the numerator and the degree of the denominator m. So I wrote it as a sub n x to the power of n all the way to a sub 0, and the denominator as b sub m x to the power of m all the way to b sub 0. If n is less than m, then there's a horizontal asymptote with the equation y equals 0. If they are identical, then a sub n over b sub m. If the difference is precisely 1, n equals m plus 1, then we have what's called slant asymptote. So this is the slant asymptote. How do you find it? Long division or synthetic division, however that it works for you, that's fine, depending upon whether you can perform a synthetic division or not. Therefore, when we look at this function, as I mentioned, the vertical asymptote is very straightforward, and the degree of the numerator is 0, the degree of the denominator is 1, y equals 0 is your horizontal asymptote. You have either horizontal asymptote or slant asymptote, not both. So here's your vertical asymptote, and I can't draw that, but this would be, and by the way, it's dashed line. So this would be your horizontal asymptote. We want to find the intercepts. That means you go here, you replace the x with 0, y with 0, you find it. So x-intercept, none. Why is that? Because f of x or y equals 0. A fractional expression is 0 when the top is 0. Since the top is a number, it can never be 0, therefore there is no x-intercept. The y-intercept, you replace the x with 0, you get 1/3. Locate at least one point on each side. So just pick up some points to the left. So remember, x is equal to -3/2. To the left of it, like -2, to the right of it, like -1. Put it back into the original function, gives you the pair. And the idea is this, because this is your horizontal asymptote, the graph either looks like this or looks like that. So those two pretty much give. So that really helps you see the graph, because it can't be both, because if it is, then it's not a function. Same thing for the other side of the vertical asymptote, either goes like that or like that. So that's why you need a couple of pairs, and that tells you how the graph looks like. I hope everybody is clear as to how we arrive at the answer. All right, so here's the next one. We want to deal with this function, finding the domain just as before. Any time you have a rational expression, find the denominator set equal to 0, exclude that. So x can't be 3. So 3 is out. Asymptotes. Well, vertical asymptote, x equals 3. That's pretty straightforward. As far as horizontal asymptote is concerned, I hope you realize the degree of the numerator is 2, the bottom is 1, so there is no horizontal asymptote, the difference is 1. You have oblique asymptote, division will give us an answer. As far as wholes concerned, there is nothing in common, it's completely factored out, therefore we don't have any wholes. So vertical asymptote, x equals 3. Horizontal asymptote, none. What about oblique asymptote? Let's multiply the two and let's divide however you want to. You get x minus 1 minus 8 over x minus 3. I'll leave it for you to get there. So y equals x minus 1 is your oblique asymptote. So here's your oblique asymptote, roughly. Here's your vertical asymptote. So basically what happens is you can find the intercept, but what happens is that the graph is here or here, here or here, and all you have to do, look at your vertical asymptote and pick up a couple of pairs on each side, you're home free. We want to find the intercepts. That means x is 0, find y, y is 0, find x. So x-intercept, that means y is 0. X-intercept happens when the top is 0. So this is -1, 0. This is 5, 0. Okay. So we have those pairs. Y-intercept, if you replace the x with 0, so you get 1 times -5. It's -5 over -3. So -5 over -3 gives you 5/3. So I hope you see that you really don't need any more points. So right here, it tells you this is the graph. Right here, it tells you this is the graph. This is the portion of the graph. It says locate at least one. You really don't need that. We have enough points. But if we don't, we can always pick up more points. As I mentioned, look at your vertical asymptote. If you have a 1, all you need a couple of pairs on each side. Sometimes even 1 will do it. If you have 2 vertical asymptotes, again, on each side of the vertical asymptote. So there are 3 subintervals. You need a couple of pairs to be on the safe side. Sketch the graph using technology. So we're not going to waste time going through that step by step. So here's the graph, roughly. Okay. I hope you realize, by the way, that if I were to draw the vertical asymptote x equals 2, so just to make it clear, this one, so VA x equals 2, HA y equals 1. So that's that. If f is 1-to-1, find the f inverse. It is 1-to-1 because it passes a horizontal line test. I hope you remember the concept of horizontal line test. A function represents a 1-to-1 function when no horizontal line crosses the graph more than once. So we can find the inverse. We've been through that. So let's quickly recap what we did previously. We've done this stuff. So we replace f of x with y. We do the cross product. So this is y over 1. So 1 times x, y times x minus 2. We can interchange x and y and do that first, or you can do it later on. So the one step is just interchange it first. So we can interchange. X becomes y, y becomes x, and now we do the cross product. Since we are solving for y, we're going to move things around by moving the y this way, negative 2x that way. And we can divide both sides by x minus 1. This is the y or f inverse. And here's the graph again using technology. Notice, and this might be interesting, notice that VA is x equals 1 and HA is y equals 2. So take a look. Let me just. So the graph goes, and it's always a dash line. So VA was x equals 2. That's why HA is y equals 2. HA was y equals 1, and it's x equals 1. So right away, it tells you that, it's working out. Also, the domain and range. The domain here, x can't be 2. So that must be the range for this guy. Over here, the domain x can't be 1, so that must be the range for this guy. So domain of f, everything except 2. Okay. Domain of f inverse. Let me erase this so we can see what we have here. So x minus 1 equal to 0 and exclude 1. So that's the domain of f inverse. Range of f is domain of f inverse. Range of f is domain of f inverse. Range of f inverse is domain of f, based on the facts that we know about inverse functions. Solve the following inequality and graph the solution set, write it in interval notation. First and foremost, we have to factor everything. So let's factor the top, because the denominator we don't need to. Now, in order for you to find the answer, there are 2 ways. You can graph the function and answer it, or go with the sign graph. The easiest way is the sign graph. You set the top equal to 0, x becomes negative 3, x becomes 6. You set the bottom equal to 0, x equals negative 2. So right here, there are 3 important points. So from here, the subintervals, x equals negative 3, positive 6, negative 2. So we are going to go with the subintervals as follows. At x equals negative 3, the function, if we call it f of x, we are calling this f of x. At negative 3 is 0, at negative 2 is undefined, and at 6 is also 0. Now, Because each one has exponent 1, honestly, if you evaluate just one of them, the rest alternate, okay? But in any event, if you pick a number, probably the easiest one would be between -2 and 6, which is 0. If you pick 0 as your test point here, I'm going to call it TP, short for test point, and put it here and observe what happens. So because you're replacing x with 0, this becomes positive, negative, positive. Positive times negative times over positive is negative. So this becomes negative. You can test the rest of them, but as I said, because each one has degree 1, they alternate. So if this is negative, then this is positive, positive, negative. We have all of those. Now going back to the question, what is it that we want? We want larger than or equal to 0. So wherever you see the positive, that's your answer. So from -3 to -2, union 6 to infinity. Okay. It has the equality. -3 is included, yes. -2 is included, no. Why not? Because it makes the denominator 0. 6 is included, yes. It makes the numerator 0. And so we write it either like this or like that. This is on a number line, and this is the interval notation. We want to graph the function using the end behavior and behavior near and x-intercept. So let's discuss the concept and let's remind everybody about the end behavior. The end behavior of a function depends on the leading term and its coefficient. That's really the bottom line. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of a function as such, which is like a sub n x to the power of n. So if the degree is even and the leading coefficient is positive, ultimately it looks like x squared. So that means the first and the second quadrant. That's the idea of end behavior. In other words, x goes to infinity or negative infinity makes no difference. In both cases, f of x or y goes to infinity. If the leading coefficient is negative, looks like negative x squared. You don't have to memorize that. Just remember negative x squared and it becomes fairly simple, meaning either x goes to infinity or negative infinity y, or f of x goes to negative infinity. In the case of a y equals x cubed, again, if the degree is odd, looks like y equals x cubed. If the coefficient is positive, that means the first and the third quadrant for the end behavior. If it's negative, looks like y equals negative x cubed, which means the second and the fourth quadrant for the end behavior. So that's the idea behind the end behavior. What happens when x blows up to infinity or negative infinity? On the other hand, behavior near is 0. It depends on the multiplicity. X minus c to the power of m, m is the multiplicity. If m is odd, f crosses the x-axis. If it's even, it doesn't. It's that simple. So take a look at this one. If you have 1 0, a single 0, okay, multiplicity of 2, multiplicity of 3. So in general, an odd versus even. The higher the multiplicity, the flatter the curve is at the 0. So that's the idea behind that. Now, putting all of them together, the very first thing we need to do is to factor this, and factoring, all you have to do, put these two together. This is really not too bad. Put these two together. And because this is x minus 5, if we take out minus sign, we get the same thing, which becomes x minus 5 times x squared minus 1, which is x plus 1, x minus 1. So now that we have the factored form, it can help us graph. So right away, negative 1, 0, 1, 0, 5, 0. Those are the x-intercepts. The y-intercept, replace the x with 0, you get positive 1, negative 1, negative 5. Their product is positive 5. So right away, you have really 4 pairs. If you draw those pairs, and look at this one is x cubed, so you have an idea how the end behavior looks like, right? The first and the third quadrant. So take a look. We have those pairs. We have this one and the end behavior. And that's all there's to it. Compare that to question number 14. And we're going to do the same thing. We have the intercepts 2, 0, negative 3 halves, 0. But this one has a multiplicity 2. We also have the y-intercept at x equals 0. When we put 0 here, this becomes minus 2 squared, which is 4 times 3, which is 12. So I'm going to graph this, a rough sketch by hand, then I show you a better graph. So let's do this together quickly. If I were to graph this roughly, this is not going to be to scale, okay? Let's assume this is 0, 12, which is not, okay? So negative 3 halves, so let's say this is negative 1.5 or negative 3 halves, 0. We have 2, 0, let's say it's 2, 0. And the end behavior is the same as the previous one because it is 2x cubed. I hope you realize this becomes 2x cubed. You don't even have to write the rest of them. What matters is you understand it's x cubed with the coefficient, leading coefficient, which is positive. And so it comes down here. But remember what's happening here. So what I'm going to do for this one, in fact, I'm going to go like this. This is the notation that is used in calculus. Because remember, at 2, it has a multiplicity 2, so it has to come back up. It can't penetrate. It can't cross the x-axis. So it goes up and comes back up at some point. And by the way, whether it comes back at this point or some other point, we need to know more to find out. Normally with the calculus, we know that. So this is a rough sketch. If you were to do it by hand, of course, you can always pick up a few more points to be on the safe side. A better graph, of course, is here. As you can see, the graph doesn't cross this function. It gets to the y, so it starts somewhere here, hits that, comes up, the y-intercept, and it crosses the second x-intercept at negative 3 halves or negative 1.50. Here's the next one. What is the least possible degree? Well, 1, 2, 3. There are 3 terms, so it has to be 4. We want to write the equation. Well, we write, okay, this one, and this one. So this one happens at negative 3, everybody. So this is x plus 3. This is x plus 2. This is x minus 1. Now this one is to the second power because it doesn't cross. So what sits in front? We don't know. We put the a in front. So take a look at what we are going to do. This a, because we don't know what is the leading coefficient. X plus 3 from here, x plus 2 from here, x minus 1 from here, and this one has exponent 2. And notice this is of degree 4. This point has coordinates 0, 3. We're going to plug in. So this is 0. So 3 times 2, 6. -1 squared is +1. This whole thing is number 6, divide by it, and you get 1/2. So A is 1/2, everybody. We want to find the degree, leading coefficient, and the maximum number of real zeros for this function. So what do? Well, first and foremost, we have to put that in descending order to make a decision. So when we put it in descending order, this comes first. So this is your leading term, which means we want to answer the question, what is the degree? 7. What is the leading coefficient? Number 4. Maximum number of real zeros, again, maximum is number 7. And behavior, well, what is this? Odd. What is this? Positive. Because it's of degree odd and positive leading coefficient, it really follows like x cubed. So because of this, looks like x cubed. So whatever x cubed is, that means x goes to -infinity, y or f of x. Remember, this is y, everybody. When x goes to infinity, f of x or y also go to infinity. So that's the importance of that. We want to find a formula for this exponential function. F of x is ab to the power of x, and 2 pairs are given. What really matters is for us to understand we have now, if we plug in a system of equations, so plug in this one, plug in this one, you have the following system, which means you have 2 variables with 2 equations. The equations happen to be nonlinear. The first one is very straightforward. B to the power of 0 is 1, so A becomes 2000. Let's just do that. This goes to 1. So A becomes 2000, which means your function f of x is 2000 times b to the power of x. So that's the meaning of that. Now let's plug it in here, replace the A with 2000, see what happens. So 2000b squared is 20. If we divide by 2000, b squared becomes 1/100. And there are 2 answers. I want you to know there is positive and negative 1/10, but the base can only be positive. Okay, that's why I just wrote the positive. There are 2 answers. We only use the positive one, and here's your final answer. All right, in this case, we have $10,250. We want to put in an account that gives us 4% compounded interest. And we want to know how much we have at the end of 10 years if it's compounded monthly. So first and foremost, let's see what's given. As we look at this formula, let's look at this one. P is the principal or the original amount, happen to be 10,250. R, the rate is 0.04 or 4%. T happened to be 10. So first let's write, according to this part, P is this, R is that. Okay, that's the given. Now for part A, so let's write the formula. Let's write the formula in general, meaning let's replace the P, let's replace the R. Now what about N? For part A monthly, so N is the number of times compounding takes place per year, so n becomes 12. So let's replace the n with 12. So for this case, n is 12. You do the math, you put it into a calculator, it gives you an answer. So the key being here. The next one, we're going to repeat the same thing, but this time weekly. N is 52. And again, we put it into a calculator, it gives us an answer. Now, what happens is if it's compounded continuously, we use a different formula. Exponential growth. So plug in P equals 10,250, R is 0.04, do the math. And there you have it. Notice the numbers are getting larger because we are compounding it more often, monthly, weekly, and continuously. How do we find the doubling time? In general, doubling time refers to the time it takes for the original amount to double. You don't even have to know what's the original amount. So if you look at this one, the idea is that P goes to 2P. So you drop the common factor of P, you look at this one. If you take a natural log of both sides, you get ln2 equals RT. If you want to solve for R, you divide by T. If you want to solve for T, you divide by R. Now, what was R? 4%. So it takes a little bit more than 17 years to achieve that. We are given a bunch of exponential functions. I'm going to remind you in general that the base must be positive, class. Okay, when the base is positive, looks like that. When the exponential growth like DEF, and if it's negative, looks like ABC. Okay, so let's just do this. If we go with, generally speaking, this is y equal to, let's say, a to the power of x, where a is positive. Or specifically larger than 1. If we, let's say, go like that, a is between 0 and 1. So having said that, which graph has the largest value of b? We are looking at the b. We are interested in the base. The base basically is the largest for these numbers. They pick up like that and they go to infinity. Now, the one that is closest to the y on the right side of the x-axis happen to be d, therefore graph d. So closest to y-axis on the right side. Which one is the smallest one? When we go here, in essence, they become, you can think of them as getting smaller and smaller again as they become closer and closer. So closest to y-axis on the left, C. Okay, so there are several of those. C is closest to the y-axis. So a quick recap. For the base to be largest, we are looking at the right side and the one closest to the y-axis. The smallest one, we are looking at the left side, the small ones, and the one which is closest to the y. It's between 0 and 1, remember that. Now we want to know the value of a. If you look at a, what does it represent? If you replace the x with 0, when x is 0, you have the y-intercept. So if we replace it with 0, this becomes 1, and 0a is your y-intercept. So we want the largest value of a, we want the largest value for the y-intercept. So take a look, which one has the largest y-intercept. So first understand that 0a represents the y-intercept. So take a look at this one. This is a y-intercept, this is a y-intercept, this is a y-intercept. Let me actually pinpoint all the y-intercepts. This is for one of them. This is for one of them. This is for actually two of them. This is for two of them. Which one is the largest? This guy. This is larger than the rest of them, right? So the answer is C. Now, which one is the smallest? Take a look. This is the smallest, right? F. Graph F has the smallest. I'm going to use transformation of f of x equals 2 to the power of x to come up with A and B, state the horizontal asymptote, domain, range, and you name it. So let's start with 2 to the power of x, which looks like this. And again, as long as you know a rough graph, that's good enough. So when we look at part A, what happens is that we are changing the x to negative x. So when you changing x to negative x, you're reflecting it with respect to the y-axis. You get the following graph. So I hope you see that when you get the following graph, practically the domain doesn't change, which is negative to positive infinity. The range doesn't change, which is 0 to infinity. The horizontal asymptote, that was the x-axis or y equals 0, doesn't change. So practically everything remains the same. Difference is this is an exponential growth, this is an exponential decay. Now, what about this one? We're going to use the same thing and shift up by 1, looking like that. So as a result, we have a new asymptote. So y equals 0 was the old asymptote. The new one is y equals 1. So the effect is not on the domain. The domain is the same. But the range is not from 0 to infinity. Now it's from 1 to infinity. So that would be the change. It does have an effect on the range. We are given the function f of x or y equals 4 to the power of x, and we want to shift that 3 units up. So add 3. Now we want to take it 5 units. We are going back to this 5 units left. So we change the x to x plus 5. Reflected about the x-axis. When you want to reflect it about the x-axis, you change the y. Okay, so you put the negative in front of a y or in front of 4 to the power of x. So it becomes minus 4 to the power of x. However, when you want to reflect it about the y-axis, then this is the y, you go from right to left, let's say. So you change the x to minus x. That's how you do that. Now, we had y or f of x equals 2 to the power of x. Now we have this graph. We want to see what we did to come up with that. So first and foremost, let's graph that. Again, y or f of x equals 2 to the power of x looks like that. This is a rough sketch. Doesn't have to be perfect. So it seems that this has shifted. Okay, this has flipped over, okay, with respect to the x-axis. And then it seems that it has gone up by so many points because the horizontal asymptote has changed. So first and foremost, it has flipped over with respect to the x-axis. Then it's been shifted up by 3 units, which indicates y equals 3 as the new horizontal asymptote. Rewriting each equation in exponential form. So how do we deal with logs is pretty straightforward. I'm going to go with this arrow, and you just follow that arrow. You can write all of them. So 5 to the power of q is m. E to the power of z is v. When the base is missing, that means common log 10 to the power of t is w. We want to go with the log. Log y base 3 is x. Now this is e, so it's ln. Ln of h is k, 100. So log base of 100 b, or log b base 100 equals a. So those are the way we write them. So why is that? Let's look at why this is the case. I want to remind you of what we have learned as far as logs are concerned. Okay. Log, if b is larger than 0 and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. So what matters, I want you to pay attention to this. In both cases, they have the same base b. In both cases, they have the same exponent y. So log is simply an exponent. Log is simply an exponent. I do that all the time, so let me just quickly go over that for you too. If, let's say, somebody says, what 5 to what power is 25? It's the same as asking log base 5 of 25 is equal to what? And they both have the answer, of course, 2. So log is simply an exponent. So take a look at the general form. Y is log x base b, b to the power of y is x. So log 1 base b is 0. That means when the argument of log is 1, we always get 0. Number 2, log b base b is 1. When the argument and the base are the same, the answer is 1. Numbers 3 and 4, log base b of b to the power of x is x. B to the power of log x base b of b is x. That means logarithmic functions and exponential functions undo each other. They are inverse functions. Log x, y is log x plus log y, the same base, whatever it might be, for example, b. This is a product rule. This is a quotient rule. Log x over y is log x minus log y, same base, repeat the same base, b. In this case, the power rule, log x to the power of n is n log x, same base, and n sits in front. Now, if you're comfortable with this, when we go with natural log and the base changes to e, you should be able to make this transition nice and easy. So this becomes ln1, this becomes ln b becomes ln e, these two ln of e to the power of x, or e to the power of n of x is x, and this last 3, instead of log, you just use ln. For common log, the base is 10. So log 1 is 0. Now, log base b of b becomes log 10 because you know the base is 10. These two, log of 10 to the power of x, or 10 to the power of log x is x. And these 3 just drop the base. I hope you're comfortable with that, because you need to be comfortable to move on from here. So let's look at this simple example. We want to state the domain, vertical asymptote, and the end behavior. In general, the vertical asymptote, you set the statement equal to 0, you come up with the answer. But the idea is, notice what happens if you have this one. Perhaps a quick graph, doesn't have to be with details, will help you answer that. Therefore, we are looking at the same as log x that has been shifted to the right by 7 units. The result is we can now, from the graph, answer, for example, the vertical asymptote, which is normally the y-axis. Now it's been shifted. So, and remember the y-axis x equals 0, now x equals 7, just as an example. The range doesn't change, it's all real numbers, but the domain changes from 0 to infinity to 7 to infinity. Therefore, let's write it. Domain 7 to infinity, range negative to positive infinity, vertical asymptote x equals 7. The end behavior class, when x approaches 7, f of x goes to negative infinity. I want to make sure everybody understands, when we say 7, really 7 from the right. It's not just 7. That's why in calculus, we write down a plus sign here. That means from the right of 7. And of course, when x goes to infinity, so does y. Now, ln of 2 minus x, we write it, we're starting with ln x. Then we change the x to minus x. Okay. That flips over with respect to the y-axis. And then we shift that 2 units to the right, which is the same as this one. So understand this one and the graph. And now the graph can tell you the information about the domain, range, and the rest of it. So the domain from negative infinity to 2, range is not changing. The vertical asymptote, you can even set this one equal to 0, x equals 2. The end behavior, when x goes to 2, g of x goes to negative infinity. When x goes to negative infinity, g goes to positive infinity. And again, I want to put this here. By 2, we really, in calculus, we would show it like that, meaning when we approach, here's number 2, when we approach 2 from the left side, okay, from the left side. Now, this one contains several transition and transformation. First, starting with log, then we multiply it by 3. Then to get to 3x minus 4, we factor out the 3. It becomes 3 times x minus 4/3. Then we have a negative, then we have a positive 3. So let's write all of them. So first we have a log, and we make it log of 3x. So it's been getting larger by a factor of 3. It's been expanded by a factor of 3. Now 3x minus 4, we factor out the 3, we get minus 4/3. That means it's been shifted to the right by 4/3. And that's important. What is your asymptote? Set this one equal to 0, x equals 4/3. Now this negative acts and it flips over. It flips over with respect to the x-axis. Then plus 3 acts and it shifts up by 3 units. So those are the transformations. I highly recommend you look at them to see what happens. So it has an effect. The domain goes then from 3x minus 4, setting it equal to 0, 4/3, from 4/3 to infinity, but the range is all real numbers. Your vertical asymptote is this line, or 3x minus 4 equal to 0, or x equals 4/3. Now the end behavior, as x goes to 4/3, the function goes to infinity. And as x goes to negative infinity, h of x goes to infinity. So what I want to write down here, this is as x goes to infinity. Let me fix things here. 4/3. First of all, 4/3 really from the right. As x goes to infinity, h of x goes to minus infinity. So x goes to infinity, y, which is the same as h of x, goes to negative infinity. I want you to know that this goes like this. It goes to negative infinity, everybody. Negative infinity. I can't emphasize this enough. All right. Here's the expansion that, again, we have here for you. This is very simple. A product rule. So log of x plus log of y plus log of z, all of them use the same base, namely 7. This is how you expand. Ln of the top minus ln of the bottom. 10 sits in front. Log of the top minus log of the bottom. I normally do it in one shot, but let me just show you the first shot. If you want, you can write log of the top, a squared b to the power of 4, same base, minus log base x of c to the power of 7. So now this one would be log of a squared plus log of b to the power of 4. So 2 sits in front, 4 sits in front, and this one 7 sits in front. So individually, okay? So this is log of a squared. So 2 log a, same base. All of them will have the same base class. Plus log of b to the power of 4. So 4 log of b, and 7 sits in front minus 7 log of c. All of them take the same base, namely x. What about here? We can write this as x cubed y to the power of 5 to the power of 1/2, and we can put the 1/2 in front. We can say 1/2 log of x cubed with the y to the power of 5. Now this is 3 log x, this is 5 log x, and both get multiplied by 1/2. Okay, so this one separated from this one with the plus sign. Don't forget there's a 1/2. Now, this is very straightforward. Ln of the top is ln x minus ln of the bottom, and you can't do anything to further separate them. Okay, let's take a couple of steps here. We can write this as log base 4 of square root of x plus log base 4 of cube root of 10y minus log base 4 of z to the power of 10. Now, I don't want to rewrite this stuff. So this one is x to the power of 1/2. This one is 10y to the power of 1/3. And therefore, 1/2 sits in front, 1/3 sits in front, 10 sits in front. This one, we can separate the 10 from the y. So let's look at it one more time. So 1/2 log of x base 4. In this case, 1/3 log 10y base 4. Maybe I write that for you. So this part is 1/3 log base 4 of 10y and becomes this. Finally, the last one, 10 sits in front. Now let's go back and put them together. To put them together, we're going to multiply these two. So 2x to the power of 4 times 3x to the power of 5 gives us 6x to the power of 9. So I'm not writing the middle term. There is one here really, so multiply these two. For this one, divide. So let me write this. So this becomes ln of 6x to the power of 9 over x squared, and we can simplify it into 6x to the power of 7. Okay. This one, I'm going to put the 2 here. This one, I'm going to put the 3 here. And now I'm going to use the product. The next one, I'm going to make this square root of y and drop the 1/2. We can do it in really one shot. Anything that has a positive goes at top. And this one, we drop the 3, we put it here. Now, this has a positive sign, this has a positive sign. So x times z cubed. This has a negative sign, it goes down. If you want, you can do them in 2 shots as follows. This one and this one, we can write log x z cubed minus log of square root of y, and here's the final answer. Let's look at some equations. Basically, the same base, we must have the same exponent. If they have the same exponent, we must have the same base. We have the same base 5, so the exponents must be the same. We bring the negative x, we make it positive x, and negative 4x is negative 3x. Or you can take the equals 3 and x is negative 1. So however you look at it, minus 1 equals x or x equals negative 1 makes no difference. Part B, we don't have the same base. But we notice that this has 64. With base 4, we can make it into 4 cubed. This has base 4. This one is 4 squared. Therefore, 3 plus 3x equals 2. Subtract the 3, you get 1. X is 1/3. Minus 1/3. X is minus 1/3. Subtract the 3, you get negative 1, negative 1/3. Divide by 2. Take a natural log of both sides. ln of the left is equal to the ln of the right. ln of the left is 3x. So divide the right side by 3, or 1/3 of that is the answer. This is the precise answer. This is a rough estimate. So you want to answer both of them. Notice this means e to the power of x to the second power. Therefore, you can factor writing e to the power of x. You want 2 numbers, the product is -6, the sum is -1. I hope you realize you can do that. Therefore, e to the power of x is either 3 or -2. E to the power of x equals -2 can't happen. So the first one is the only one that we can work on. Take a natural log of both sides. If I take a ln x of the left side, I get x, and the right side is ln 3. Again, precise answer is ln 3. Rough estimate of 1.0986. All right. 3 squared is 9k. Anytime you have a log and a number, you have to go to a definition. By the way, x equals y. Logs can be equal as long as they have the same base or the same argument. So if they have the same base, they must have the same argument. That's what it says here. If they have the same argument, they must have the same base. That's the idea behind that. Therefore, 3 squared is 9k, and k becomes 1. Log of 4 times minus 5x, which means log of minus 20x, is 2. Now we go to the definition. Minus 2x is 10 squared. Minus 20x is 10 squared. And x is -5. Notice if you choose x to be -5, then this becomes positive because it must be positive or it doesn't work. That's important to check. All right, these two have the same base, so they must have the same argument. All you have to do, again, log, nothing else. So 5n minus 2 must be 8 minus 5n. This is a simple case. You can move things around. This one comes here, becomes positive 5n is 10n. 2 comes here, becomes positive 10n becomes 1. Whenever you have logs all over the map, then you have to bring each side to a single log. This one is fine, this one is not. Put them together. X times 12 gives you 12x. So now the left side was fine. The right side is also a log of a single argument. So because they have the same base, namely 10, they are common logs, then x plus 12 and 12x, their argument must be the same. This is simple. You subtract the x, you get 11x, you divide by it, you get to the answer. I can write that. So this one makes this one 11x. Okay, we see logs and nothing else. So let's put each side into a single log. This is fine. The left side is ln of x plus 4 over ln x. Ln of x plus 4 over x. Now we have the same base, namely e. We must have the same argument. So this is an equation we're going to solve by cross product. Remember, this is x plus 4. This is x times x, x squared, x times 1x. We are going to drop the x squared becomes 4. Therefore, x is positive or negative 2. However, let's go back here. If I put the negative 2 here, I'm fine because I get positive 2. But over here, it's not. None of the arguments can be 0 or negative. Remember, they all must be positive. So this is out. So go back to the original one and check it out. For this equation, one side has a bunch of logs. Let's put them together. X times x minus 1. Okay. The right side is a number. There's nothing else you can do. Now you go to the definition. 2 to the power of 1 is x times x minus 1. You are going to solve this simple equation. Distribute x squared minus x equals 2. Subtract the 2, bring them to the same side, factor, and solve. So x minus 2, x plus 1, there are two answers. X is either 2 or negative 1. Now, as always, we check with the original equation. If I put number 2, it's fine. This is fine. But if I put negative 1, this is not fine. I don't even have to check the next one. As long as one of them is no good, it's out. So negative 1 is not working. So therefore, it's out. Four to the power of x plus 10 equals 3. We want to solve this. First, we want to isolate 4 to the power of x by moving 10. Exponential, it doesn't matter. 4 to the power of x, e to the power of x, whatever it is. Can it be negative? No. If you remember, the range is from 0 to infinity. This has no solutions. This one, 7 to some power is 1. That must be 0 because 7 to the power of 0 or anything to the power of 0 is 1. Therefore, x minus 10 must be 0. And x must be 10. Four to the power of x is 9 to the power of x minus 2. Now we want the same base. We don't have it. So what do? Basically, we have to take the log, either natural log or common log of both sides. It makes no difference. So let's take a natural log. So x becomes the coefficient, in this case, x minus 2. Please understand ln 4 and ln 9 are not missing. Those are numbers, but we want to keep them as such because it gives us a precise answer. To solve for x, we're going to distribute the right side. To solve for x, We're going to put the x's together. So we can move this one this way. Now factor out the x. Divide by the parentheses. Now this is the precise answer. Two things I want to explain. Number one, depending upon how you did the move, this could be, take a look at this negative. This could be 2 ln 9 over ln 9 minus ln 4. I hope you see they are identical. And number two, this is the precise answer, which means what about the approximation class? You can do the approximation by plugging it. I have a bonus question. Since we have time, I'm going to go over that. Here's what we have. I thought it's an interesting question. Assume log 2 with some base. We don't have a base is A, log 3 with the same base is B, and log 5 is C. All of them have some base, B, which we don't know what they are. Can we evaluate those knowing the fact that log 2 is A, log 3 is B, log 5 is C? Well, all you have to do, factor the numbers such that they involve those basic numbers 2, 3, 5. So 50, I hope you know that is 2 times 25, 2 times 5 squared. Therefore, it's log 2 plus 2 log 5, both of them base B. Replace, and you have the answer. Replace, and you have the answer. What about this one? We do exactly the same thing. This is 300 to the power of 1/5. So 1/5 sits in front. So that's the first thing. Now, 300, every 0 corresponds to 2 times 5. So this is 2 times 5, this is 2 times 5, this is 3. I'm showing you a very fast way of factoring. So we have 2 squared times 3 times 5 squared. So I'm going to repeat. A 0, that means 10, corresponds to 2 times 5. So this is 2 times 5, this is 2 times 5. That's why we have 2 squared and 5 squared, and this is 3. Now, we're going to expand this. 1/5 log base B of 2 squared times 3 times 5 squared. So 2 log 2 plus log 3 plus 2 log 5, all of them the same base B. So we are expanding. And we're going to replace them, A, B, C. And that's the final answer.